Hey everybody, here we are today. Today what I'm doing is not necessarily the lecture lesson, but I am going to kind of go through a lab with you. So I'm hopefully going to see how this works. My goal at the end of this is for me to kind of make a quick little introduction like I normally would during the lab, explain to you what's going on. Then I'm going to go out and have to do the lab, which I really would rather have you guys doing, but I don't know what we're going to be allowed to do. And then what I'm going to do is I'm going to bring that data back, and then I'm going to allow you to kind of go through and do the lab report. Now, why am I making you do this? Because I think it really brings together a lot of the higher level thinking that's required to understand these certain concepts. So what's the lab we're covering today? Well, it is our primary productivity lab. It's a lab I always do in the beginning of the year because it helps us to really understand the idea of energy within an ecosystem, and how productivity works. So I'm going to go sit kind of up at my computer because I'm going to be doing a lot of drawing with this lessons, and I don't think it's going to be too long, so please bear with me. Alrighty, so our primary productivity lab. The first thing we need to understand about productivity is photosynthesis. Most of you should be familiar with photosynthesis. It shouldn't be anything new, but the idea, this is your photosynthetic equation up here. The idea that carbon dioxide plus water will yield sugar and oxygen when sunlight's present, enough solar energy coming in. Now, we also know that the relationship between photosynthesis and then aerobic cellular respiration, which is the equation below it here, is just the opposite. You know that there is sugar that you must ingest. As a heterotroph, you have to go and consume other organisms, but autotrophs also will go through this. That's why they produce sugar. That's why we have to understand that in order for autotrophs to grow, they have to go through photosynthesis to produce the sugar. And actually, they will consume most of it themselves and through their metabolic processes. But when we talk about aerobic cellular respiration, we're talking about taking glucose plus oxygen. That's why we need to get oxygen to our muscles to make sure we are going through as efficient a form of respiration as possible, because we know aerobic respiration is far more efficient than anaerobic respiration. And what will eventually happen is we will form carbon dioxide and water. Now, the one thing that you don't see, and it's not mentioned in here, is what we call the micronutrients that are associated with photosynthesis. Things that we need, different other elements. We need nitrogen, you need phosphorus, and you need potassium. These three things are what make up most fertilizers. But when you read the lab, you will read about the full photosynthetic equation and how much nitrates, phosphates, and other compounds are needed in order for it to grow. These are our limiting reactants. So there are limiting reactants. They control the rate of the photosynthetic equation. If they are in abundance, we'd go through a lot of photosynthesis. If they are not in abundance, we slow down the rate of our photosynthesis. And pretty much what we are going to be looking at through this lab is this right here. Because we can look and determine how eutrophic something is, meaning how much nutrients it has. If it has nutrients in abundance, we consider it eutrophic, E-U-T-R-O-P-H-I-C. All right. Eutrophic means that you have too many nutrients. It can lead to things like harmful algal blooms and other areas where we have too much vegetation growing. Or on the converse, if you don't have enough nitrogen and phosphates or enough of these limiting reactants, you could be what's called oligotrophic. And oligotrophic is pretty much going to be a sterile ecosystem because it no longer has those limiting reactants. One of the things, if you're not familiar with it, I want to kind of make sure I go through the aquatic food chain and the way it works. We start with energy coming in from the sun. It starts with phytoplankton. Phytoplankton are your photosynthetic plankton. And then they are consumed by zooplankton, which then eventually are consumed by bigger and bigger organisms. All righty. Now, the idea of productivity. There's two different types of productivity. Hopefully you remember from the lesson that I just taught you. Right? The idea of gross primary productivity and net primary productivity. Gross primary productivity is just pretty much the rate of photosynthesis occurring. So it's how efficient can an organism convert solar energy with those reactants into organic matter. And then eventually it goes and produces, it gets our net primary production, which is the amount of our GPP minus our cellular respiration amount. So that's the big difference there. It's pretty much how much are you using to grow and to facilitate life versus how much are you generating. Now, if an organism or if an ecosystem is generating a plethora of organic matter, it can then support more and more upper level predators. All right. If it's barely producing enough to sustain, it's probably right where it's at. It can't support more organisms. If it's producing less, if it is a negative yield, all right, meaning that it's producing less and less biomass because things are dying off, things are being eaten, consumed, whatnot. It means the food web ecosystem structure is way off and it's not sustainable, and that whole ecosystem will collapse. So what we are going to do is take that premise, the idea of looking at how productive an ecosystem is, and translate it to the Neshaminy Creek. And hopefully what we're going to see is if Neshaminy Creek is overly productive, meaning that it could support more life, is it right around equilibrium where it's kind of right where it's supposed to be? Or is it on the converse? Is it detrimental? Is it negative? And needs more support and it needs to cut back on the amount of organisms in there? So hopefully we'll see that. Now, how are we going to do that? Well, we're going to use some tools here. Here are my tools. 2 bottles. One of them is clear. The other one is wrapped in tin foil. Now, what I'm going to do is I'm going to take this big apparatus here. This is just a piece of wood, a piece of styrofoam, and a heavy weight attached to it. And what I'm going to do is build a rig to hold these 2 bottles in the water. So what we're going to do, let me draw it out here, is I'm going to build my float at the top. So that's my float. And it's going to have an anchor that comes off of it, and that's that heavy weight. So that's just designed to stop it from washing away and staying where I put it. Right? So that's has nothing to do with the experiment, just actually the setup of the experiment. Then attached to the float on equal length ropes, I'm going to have the bottles. Bottle here and a bottle over here. All right, so far you're with me. My 2 bottles on a float with an anchor. Now, one of them is going to be dark, so I'm just going to color that in real quick. All right, so you understand. Now, what I'm going to do is the first thing I'm going to do is I'm going to rinse these out thoroughly. They're going to be clean, completely dry before I even start with anything. Make sure they're free of all other chemicals, whatnot. And then what I'm going to do is when I get down to the creek, I'm going to rinse them in the creek water so that I flush creek water in there as well. Then what I will do is I will start with something called the initial DO. And DO stands for dissolved oxygen. Because what we're really looking at is the amount of oxygen in the water. Now, what I'm going to do is I'm going to fill these jars up with the same water. So I'll just kind of submerge them at the same spot in the creek so that they fill up with water. And then what I'm going to have is I'm going to have initial dissolved oxygen reading. Now that initial dissolved oxygen reading will be the same for both of these. And what I'm going to do is I'm going to let this sit on a sunny day for 24 hours. So I'll put this in the water, and then I'm going to come back the next day and record and retrieve this and then record some more results from it. So after sitting for 24 hours, I'm then going to take these 2 bottles and very, very carefully, I'm going to open them up as not to expose much extra air into them. Oh, I forgot one thing. When I go to fill them, I'm going to fill them underwater. So I'm going to actually completely get all the air out of this. And then what I'm going to do is cap it underwater so that I make sure it has no oxygen inside of it, no air bubbles, because air bubbles can really alter my data. So I want only Neshaminy Creek water in that jar. Now, after sitting for 24 hours, what I'm going to do is I'm going to retrieve these and I'm going to carefully take the dissolved oxygen again. So I'm going to take dissolved oxygen. I'm going to have what I'm going to call my light bottle. I'm just going to represent that as a DLB. And then I'm going to have my dark bottle, and I'll write the word dark out here. Right? So what I'm going to have now is, in theory, 2 different dissolved oxygen levels. Now, why? Well, let me go to a new slide that's a little cleaner here. So I have I'm just going to represent the bottles with a circle right now. Okay, so I have my light bottle, and I'll have my dark bottle. In the light bottle, sunlight can come into it. So what's going to happen inside here? Well, photosynthesis will take place. Right? But not only photosynthesis, it's also going to go through cellular respiration because those phytoplanktonic organisms are going to be going through cellular respiration. They're trying to grow. In the dark bottle, sunlight cannot get in. So sunlight is going to be rejected, so it is not able to get inside. So the only thing happening inside of here will be cellular respiration. So what I'm pretty much doing is I'm figuring out the rate of photosynthesis of Neshaminy Creek. And how am I going to measure that rate? Well, we know that one of the byproducts of photosynthesis is oxygen. So what I am going to do is be able to compare the dissolved oxygen in the light bottle versus the dissolved oxygen in the dark bottle to tell me then through some advanced calculations how productive the Neshaminy Creek ecosystem is. Hopefully this works out. Hopefully you understand what I'm talking about, and I probably will be next talking to you when I'm down at the Neshaminy Creek getting ready to perform my dissolved oxygen test and get the apparatus set up. Thanks for checking in. All right, welcome back everybody. Here we are today. We are doing the first part of our primary productivity lab. So what that is going to require us to do is to get a couple pieces of data about the Neshaminy Creek before we go and put our apparatus into the water. Remember, our apparatus has a light bottle and a dark bottle. They're going to be filled with the identical or the same water source. And then what we are going to do is we are going to look to see if there's a difference in the dissolved oxygen after sitting for 24 hours. I'm out here early in the morning on the Neshaminy Creek, and what we are going to do is I am going to today set the apparatus in the water. I'm going to take the initial temperature of the water, and I'm also going to take a dissolved oxygen reading of the water. That is my goal today. Now, what am I going to use to do that? I've got a couple different pieces of equipment. First one, I've got a water testing kit from Lamont Chemical Company. So when you see the data, it says Lamont Chemical Company. This is the water testing kit I've used for that. The second piece of equipment I have is from Hanna, all right, and it is a digital or dissolved oxygen probe. It's a multi-probe. It's a multimeter. I'm sorry, hard to do with two hands. There we go. All right, but this will utilize the give us the dissolved oxygen reading of the creek pretty quickly. So this only takes about a minute or so to calibrate, and then it'll be ready to rock and roll. And the third way in which I'm testing is with this company. This is HACH, H-A-C-H. So when you see the 3 different test results, I am taking 3 different tests to calculate the dissolved oxygen. Why am I doing 3 different values? Because I want to make sure that I have an average or different ways, and that way I can calibrate. If I just use one, we know our potential error and potential precision could be way off, but I'm going to use all 3. I'm going to show you guys how to set up the Google Sheet, so it's going to really do the formulas for us, so it's really not like it's extra math, it's just extra work on my end collecting the data. So here we go, we're going to get started, and I'll kind of videotape along the way to see what all we get. Alright, so the first thing I'm going to do, I've got my thermometer here, I attached it to a rope. I'm going to toss it out into the water a little bit. All right, I know it's not the cleanest looking apparatus, but it will allow us to sit and collect the temperature. So I'm going to toss this out, let that sit, and then while that's collecting the temperature, I'm going to go reach down and grab a small little water sample so that I can get the initial dissolved oxygen reading. So I've got my initial water reading. I tried to be really careful when I was filling this, not to aerate the water too much. All right, and now I'm going to work really quickly because I don't want the temperature to change too fast, so that I can go and get all of the different tests done. First thing I'm going to run is the probe so that I can get that done, and then I can go and do all the chemical testing to this water. All right, so now what I've done, I've gone and I filled up my my sample bottles. I filled them when they were underwater. So as I filled them, I made sure that the water was all the way to the top, and we use these little plunger type toppers so that they seal off all the water and don't let any air bubbles inside. It's really important that I don't have any extra atmospheric air. Both of these were filled the same way. Now what I'm going to do is I'm going to tie them off to our rig, and I'm going to put the rig in the water, and we'll come back and get it tomorrow.
Now this apparatus has an extra little weight to it. So I know it looks like we're in the shade right here, which is going to be really counterproductive to the experiment. The thing is, this area will get a lot of the afternoon sun. So as the sun kind of passes over, this area will get a lot of sun. And what I'm going to do is I'm going to throw this weight to pull the apparatus out. So by putting the weight and the anchor further out, it will help to pull the apparatus further out. And then what I will do, I'll use this last leader chain or leader line to tie it off and anchor it so that I can come back tomorrow and retrieve it. I'm going to have to take a break real quick. Got myself a little bit of a knot here, so I'm going to pause the video and come back. Alright, I'm back. So I've got the knot untied, and I've got my weight here. So what I'm going to do is I'm going to toss my weight way out there, and I'm going to tie off this retrieval line to the shoreline. So hopefully this all works, and this weight will eventually, over time, pull this apparatus out further into the water. There it goes. Alright, so here we are back at the site where we left the primary productivity lab. It's been sitting for 24 hours. We had plenty of sun. I know it looks very similar to yesterday's video, but I promise you this is just the same time of the day I'm coming out here to work on this. So what I'm going to do now is I'm going to retrieve the rig and the apparatus. I'm going to very carefully pull out the two sample bottles. I don't want to expose any extra oxygen to them. And what I'm going to do is I'm going to immediately go and start sampling and running the chemical tests on them so that we can see what the dissolved oxygen value is of the light bottle versus the dark bottle. Remember, that's the whole thing. We are looking at the productivity as what is the net productivity versus the gross primary productivity, and how does it differ, especially with oxygen as a product? Because remember, oxygen is going to be produced through photosynthesis, but it's going to be consumed through cellular respiration. So in theory, after all our data is done, we should see that the dark bottle has a lower dissolved oxygen than the light bottle. Fingers crossed. Hopefully everything went well. The experiment seemed to have perfect conditions. This is ideal conditions. 24 hours of just no clouds, plenty of sunlight, nice cool temperatures. Hopefully we'll see what we want to see. So here we are with our light bottle and our dark bottle, and what I'm going to do now is just run the chemical tests on it. The first thing I'm going to do is I'm going to run the probe, then once I've got the probe done, I will run the different dissolved oxygen tests. So check back with the data in a little bit, and hopefully we'll have some answers for you. So here I am. I'm going to run the first dissolved oxygen, and we'll just show you a little bit of the reaction here. I don't want to waste all my camera battery's getting pretty low, so I don't know how much time I have, but I'm going to fill this small sampling bottle with the sample, and I'm going to do it very, very carefully as to not get any extra air in there. I don't want to agitate it too much. I'm going to overfill it because it's okay, I've got extra water. Alright, so it is completely filled up to the top. Now what I'm going to do, put a little calibrated stopper in there. Alright, and if you look, there are no air bubbles in here at all. So that is exactly what I want. So now what I do, according to the directions, I will add some chemical reagents, and we'll see how much oxygen is in here. It says tare. It's very hard to tear, so we've got some nice nail clippers here. They do the trick. All right, just kind of cut it. Allows us to rip them open. Take all my trash out, so I'm just going to pack it in the container right now. Open these guys up. Pillow pack number 1 starts. So I had that chemical reagent, all of it. And now the second chemical reagent. All of that. Now we will cap it. Get everything mixed up. Cap it, invert it a couple times, shake it up, and it's going to turn yellow if oxygen is present. So no matter what level, it will turn yellow. All right, and what's happening right now is a precipitate is forming, and eventually we'll do a titration to figure out how much oxygen is in this sample. So this will use a simple, the Hach system uses a simple pillow pack measured pre-calibrated reagents, and then we go and do a little simple titration to figure out how much oxygen is in there in milligrams per liter. The Lamont chemical test kit will use a sulfuric acid and stabilizer, and then what we will do is, again, this one's a little bit more calibrated of a titration. Again, we're looking for a color change. Sorry, my knees are hurting a little bit. I have to stretch out. We're looking for a color change, and this will sit now, let the solid the flocculant drop down and precipitate out, and then we'll sample the water above it. So hopefully you get all the data or understand how all this chemical testing is done, and we will get all the data and analyze the data in class. So thanks for checking in, and I'll see you guys in a little bit. A belted kingfisher flew by when I was doing the lab, so I figured I'd take a little look at him here. So this is that guy up in the scene here. I'm trying to focus as best I can. They'll dive head first in and catch little fish. So it's showing that Neshaminy Creek is pretty productive. Make a rattle sound when they fly. Maybe we'll watch him for another 20 seconds, see if he flies. While I was just watching this kingfisher, we just had a hawk fly in, so let's see if we can find him real quick. Up in the top of this tall sycamore right over here should be a hawk. Just flew in. Let's see if I can find him now. Where did he go? Thought it'd be easier to find. I'm sorry. We'll go back to the kingfisher. Oh, there goes the hawk. Good news. I'll never make it as a wildlife documentarian. Bad news, I'm still your teacher and we're watching this video. Come on, do something, bird. Kind of made a little noise there. Okay, that's enough for now.